Hyperbola. As we have discussed about circle, parabola, ellipse, now comes the next conic section, which is hyperbola. As we have discussed in the previous session that hyperbola is the conic section of a bicone, which we have seen when it is cut along the cone, we get the cross section, which is a hyperbola. So that hyperbola is what we're going to discuss in the session more briefly through the mathematical properties. Now, as we know that hyperbola is the locus of a point P such that its distance from the fixed point, which I denote with S, if the distance of this locus from the fixed point S is always greater than the distance from the fixed straight line. That is, if I take the distance from P to the fixed straight line L, then we say the perpendicular distance, then we say that the locus is a hyperbola. That is, if SP, which is the distance from S fixed point to the locus, and by PM, which is the perpendicular distance from P to the line fixed straight line L, is always greater, then we say the locus P follows a path which we call as hyperbola. Is how we get this in the form. That implies is the condition for existence of hyperbola. S being the fixed point, L being the fixed line, and P being the locus, SP by PM should always be greater than 1. Is how we connect the hyperbola with its mathematical inequality. Now let's see the eccentricity of hyperbola conditions. The eccentricity is generally denoted by E, which is nothing but the ratio of SP by PM. Is how we define the eccentricity. And for hyperbola, the condition is that E is greater than 1. Is how we define the eccentricity of the hyperbola. E is greater than 1 for hyperbola. Now let's see the equation of hyperbola. Before we discuss the equation of hyperbola in standard form, it is very important to understand or identify the shape of hyperbola exactly on xy coordinate system. So let's see how an hyperbola looks on an xy coordinate system. Suppose I have my x-axis and my y-axis out here with center as origin. Now an hyperbola looks something like this. It is like a biparabola where I have two parabolas on either side which are symmetric about y-axis. This is the mirror image of this with respect to y-axis. Now as I have my center as origin, my focus lies somewhere here. Then the other focus on the other side lies out here. Is how we identify the focus of these two things. Now as I have this, I take the point P on the hyperbola as this, and similarly I take the point here as P dash. Now I drop a perpendicular from P onto this line which exists out here. Say there are two lines, L and L dash out here, and I drop a perpendicular from S to P, which is M, and from P dash to M dash, which is this, which clearly show that SP is greater than PM, because for hyperbola SP is always greater than PM, and hence S dash P dash is greater than P dash M dash. Is how we understand this. So with this we identify that S dash are called the foci of the hyperbola, the plural of focus. S is the focus and S dash is the focus, and S dash are the foci of the hyperbola. And L and L dash are said to be the directrices of the hyperbola, which we have here are the directrices of the hyperbola. The center is origin. The center of hyperbola is said to be origin 0, 0 is how we identify in this case. And P and P dash are said to be the points on the hyperbola. So with this, let's define each of the standard form of equation of hyperbola using the basic information of foci, directrix, and origin. Now here, the equation of hyperbola is given by x square by a square minus y square by b square equal to 1 is how I identify the equation of hyperbola in this form, where here I assume a is greater than b and b square is a square into e square minus 1. So these are the two properties through which I define the standard form of hyperbola, where equation of hyperbola in standard form is x square by a square minus y square by b square equal to 1, with a greater than b, and b squared is given by a square times e square minus 1, where in ellipse it is 1 minus e square. Here it is e square minus 1, simply because e is greater than 1. And in case of ellipse, e is less than 1. In case of hyperbola, e is greater than 1, given by b square equals a square times e square minus 1. Equation of hyperbola in standard form. Now here, let's try to identify the coordinates of foci, equations of directrices, and any other properties identified here. Now as I have here my distance, the a is the point which the hyperbola cuts x-axis on the positive side, and a dash is the point of intersection of hyperbola with negative side of x-axis. And similarly, I have b and b dash which exist out here. Somewhere. Now, the distance a dash is 2a, which gives me the property that the coordinates of a are a0 and coordinates of a dash are minus a0, such that a dash is 2a. And then my coordinates of b are 0b and this is 0 minus b. Therefore, bb dash is 2b. And we have the foci which are given by AE, 0, and the other focus is given by minus AE, 0. Is how we identify. And then if I have this as Z, and this as Z dash, then the coordinates of Z are A by E, 0, and the coordinates of Z dash is minus A by E, 0, and center is of course origin. Is how we identify each of the coordinates of S, A, Z, C, Z dash, A dash, and S dash. And comes the equation of directrix, which is given by x equals A by E, and here the equation of directrix L dash given by x equals minus A by B, A by E. Is how we identify each of the coordinates as described out here. The focus, the vertices, the center, and foot of perpendicular of the focus with the directrix, and equations of directrix are all out here. Now let's see how we can find eccentricity as the formula. So suppose I have the equation of hyperbola is x squared by a squared minus y squared by b squared equals 1, with a greater than b, and both a and b are positive, and of course e greater than 1, then we know that the b square is given by a square into e square minus 1. So using this, let's see what would be the formula for e when I make e as the subject in this relation. So to make e as the subject, I expand the brackets on the right hand side, a square e square minus a square, which on further simplification gives us a square e square equals a square plus b square, by bringing a square arranged to the other side. That implies my e square is a square plus b square by a square. That implies my e is plus or minus root of this. But since e is greater than 1, I have e strictly as plus root of a square plus b square by a square, or I have e as root of a square plus b square by a. Is how I identify the relation with eccentricity E. Therefore, the eccentricity of the hyperbola is given by root of a square plus b square by a square, or root of a square plus b square whole over by a. The formula for eccentricity using the standard form of hyperbola condition. Now that we have discussed about some of the properties of hyperbola, now next is the x-intercepts and y-intercepts. That is, we would like to identify at what points does the hyperbola cut the x-axis, and at what points does the hyperbola cut the y-axis. So let's see the x and y-intercepts of the hyperbola. So equation of hyperbola being x squared by a squared minus y squared by b squared equal to 1, assumed with a greater than b. To find the x-intercept, I take the condition y equal to 0. So in order to find the x-intercept, I assume with y equal to 0, then I get is what we get when we simplify. That implies x is plus or minus a. It's not root a, it is a. Therefore, the graph cuts x-axis at a and minus a. Therefore, hyperbola 1 cuts x-axis at a0 and minus a0, and therefore we denote this with a and this with a dash. Is how we identify the x-intercepts of the hyperbola. Similarly, let's see the y-intercepts of the hyperbola. Now next comes the finding of y-intercepts. Now in order to find the y-intercepts, we assume x equal to 0. To find x-intercepts, y equal to 0. To find y-intercepts, x equal to 0. So let x equal to 0. Then the equation 1 reduces to 0 square by a square minus y square by b square equals 1. And this, on further simplification, gives 0 minus y square by b square equal to 1. That implies minus y square equal to b square on cross multiplication. That implies y square is minus b square. But this is not possible because root of a negative number is not defined. Therefore, since root of minus b square is not a real number, which indicates that, therefore, y-intercept do not exist. And when y-intercepts do not exist, we understand that therefore the hyperbola 1 given by equation 1 does not cut y-axis. It cuts x-axis at a and a dash, but the hyperbola does not cut y-axis because of this reason. Is how we understand the x and y-intercepts for the hyperbola. Hyperbola has two x-intercepts, a and a dash. Hyperbola does not have any y-intercepts. Now this session is about region of existence of hyperbola because it is identified that there are some regions where the hyperbola does not exist. So let's see what are the regions in which the hyperbola exists and what are the regions in xy coordinate system where the hyperbola does not exist. So in order to identify the region, let me take the equation of hyperbola in standard form. And then I would like to make y as the subject. So that implies y square by b square is x square by a square minus 1. This, on further simplification, gives y square is b square by a square times x square minus a square is what we get when I cross multiply and simplify this with LCM. That implies my y is plus or minus b by a of root x square minus a square is what we get. Now the y value is said to exist to be real. The value of y is real if and only if plus or minus b by root of x square minus a square is real. And the whole of this being equal is real only when this is positive, because root of a negative number is not defined. And therefore, this is real only if x square minus a square is at the most greater than or equal to 0. So which, on further simplification, gives x greater than or equal to a and x less than or equal to minus a. And this is the region where the parabola or the hyperbola exists. That is, if I take the hyperbola, I always have the hyperbola in the region where x is a0 and minus a0 with a dash and a. So hyperbola does not exist in this region, but it exists in this region. Is how we identify the existence of hyperbola. So this makes me understand the two regions, one this and the other is this, where hyperbola exists and here does not exist. So this is the region where the hyperbola does not exist. This is the region where the hyperbola exists. Is how we identify the relation connected with the region of existence of hyperbola. X less than or equal to a, greater than or equal to a, and x less than or equal to minus a is the region of existence of hyperbola. Now let's see the unboundedness of hyperbola. That is, if hyperbola is a closed shaped curve or an open shaped curve. So for example, the circle is a closed shaped curve, an ellipse is a closed shaped curve, but parabola is not a closed shape, but it's an open curve. Similarly, let's identify the openness or closeness of hyperbola. Now, as we have seen here, the hyperbola which exists in this manner makes us understand that as I proceed on further and further, it opens up and goes till infinity. And similarly on the left, as I see here, this goes on and on and on till infinity as I proceed towards this minus infinity out here. So this makes me understand that this is completely open, but it can never close. This end can never close with this end, and this end can never close with this end. Mathematically, which proves that if I have the equation x squared by a squared minus y squared by b squared equal to 1 as the equation of hyperbola, that implies x tends to plus or x tends to infinity when y tends to infinity, and x tends to minus infinity when y tends to minus infinity. Therefore, the curve is unbounded, which clearly shows that when x tends to infinity, y doesn't tend to a finite value but infinity, and when x tends to minus infinity, y also tends to minus infinity. That is, x tends to plus or infinity when y tends to this, implies the hyperbola is unbounded. That is, it is not a closed curve but an open curve. That is, open curve is how we understand the relation between openness and closeness. A hyperbola is an open curve and unbounded. Let's see what is the role of horizontal line to the hyperbola. As we see here, I clearly see that for this hyperbola, if I draw a horizontal line parallel to x-axis, then that cuts the hyperbola at 2 points this and this. That is P and P dash are the 2 points where this horizontal line cuts x, the hyperbola. So every horizontal line is set to intersect the hyperbola in 2 points. So for example, I take a line in this form. Then this also is set to cut the hyperbola in 2 points, Q and Q dash, and then we get this parallel to this, 2 points of intersection. So the learning outcome here is that every horizontal line parallel to x-axis cuts the hyperbola in 2 points is how we identify the property of horizontal line connected to the hyperbola. Now let's see the symmetricity of hyperbola connected with x-axis initially. So for example, I have the standard equation of hyperbola as x squared by a squared minus y squared by b squared equals 1 implies my y is given by plus or minus b by a root of x squared minus a squared from this. Therefore, this makes us understand that for every real x corresponds to 2 y values, one given by plus and the other given by this, and these two are opposite in signs, is how we understand the corresponding values. Therefore, for every x, one y lies exactly on the above and exactly on the below if I take it along y-axis. That is, if I take the hyperbola in this form, then I clearly understand that for every x there are 2 values, one on the positive side and one on the negative side. Therefore, the graph is symmetric about x-axis. That is, the symmetricity above and the symmetricity below are exactly symmetric with respect to x-axis. That's how we understand the symmetricity of the hyperbola with respect to x-axis. That implies the hyperbola is symmetric about x-axis, as can be seen here. High symmetricity of hyperbola with respect to x-axis. This acts as the mirror in reflecting the surfaces of each other. Now next is identifying the symmetricity about y-axis. So in a similar manner, I take the equation of hyperbola in standard form with this implying that my x is plus or minus a by b root of y squared plus b squared. Therefore, if I have my y, which is a real value of y, corresponds to 2 values of x, one given by a by b root of y squared plus b squared and the other given by minus a by b, this. That means every x has 2 corresponding values, which makes us indicate that I get the symmetricity about y-axis. That means they just change in opposite sign, and therefore this part of is said to be symmetric about this side. So this is how I get the symmetricity about y-axis. All the image on this right is exactly same as this, or this distance will be same as this distance, or any point you take will be exactly the reflection of that point along y-axis. That implies the hyperbola is symmetric about y-axis, is how we conclude. Therefore, finally we conclude that an hyperbola is both symmetric along x-axis and also along y-axis. Similarly, we have the ellipse, which is symmetric along x-axis and symmetric along even y-axis. A circle is symmetric about x-axis and symmetric about y-axis, and hyperbola is symmetric about x-axis, but the symmetricity about y-axis does not arise because the graph does not cross y-axis, is how we understand the concept. Now let's see the connection of the distance from focus to any point in the hyperbola, which is related with a, that is half the length of major axis. So as we know that the standard equation of hyperbola has its shape in xy coordinate system in this form. Now this hyperbola given by equation x squared by a squared minus y squared by b squared equal to 1 with a greater than b has the focus connected with a. That is, if I take any point P on the hyperbola, and if I have the focus S, which is out here, then I'll connect S with that point P on the hyperbola, and I connect the other focus connecting with this. So I have SP, the distance from focus to the point, and S dash P, the distance from other focus to the same point P, x1, y1. Then mathematically I have the relation between SP, S dash P and A, which is the distance from center to the vertex. This is A. So this distance is connected with the distance as S dash P minus SP equal to 2A. That's how we connect the relation between SP, S dash P and A. So S dash P minus SP is equal to 2A, which is a constant. And this is referred as the distance AA dash. So the distance AA dash is 2A, which is connected. So SP plus S dash P is equal to AA dash, which is 2A, or S dash P minus SP is AA dash, which is 2A. Now let's see the general notations for hyperbola. In general, the standard form of hyperbola is denoted by S identically equal to x squared by a squared minus y squared by b squared minus 1 equal to 0 is how we denote the standard equation of hyperbola. Now in this, if I take the point P x1 y1, then its corresponding S1 is defined as x1 by a squared minus y1 by b squared minus 1 equals 0 is what we get for x1 y1. If suppose I have then its corresponding S11 is denoted by x1 squared by a squared minus y1 squared by b squared minus 1 equal to, it's not equal to 0. This is a constant value. So this is a constant value. So this we don't equate to 0. So S11 is a constant value. This is an equation. This is a constant value. And this is the equation of hyperbola. And if suppose I want to find S12 corresponding to 2 points x1 y1 and x2 y2, then equation of S12 is given by x1 x2 by a squared minus y1 y2 by b squared minus 1 is how we define the different types of notations which we have, which is hyperbola, which is a linear straight line, which is a constant value and a constant value. Notations for hyperbola are denoted with S, S1, S11, S12, S22, etc. Transverse and conjugate axis. What are these two axes for the hyperbola? Let's see through the ellipse in standard form. Say I have the equation of ellipse in standard form with y-axis and x-axis. This is A and A dash and B and B dash. Then the distance between A dash is 2A and the distance between B and B dash is 2B, and usually the line which consists of A dash is called the transverse axis, because this axis passes through A dash, and the line which passes through B and B dash is called the conjugate axis. So in case of standard equation of hyperbola, this is transverse axis and this is conjugate axis. For the hyperbola, x squared by a squared minus y squared by b squared equal to 1. So the transverse axis equation is given by y equal to 0 and conjugate axis equation is given by x equal to 0. That is, the x-axis is the transverse axis and y-axis is the conjugate axis. Now next is about length of transverse and conjugate axis. So now that we have discussed about transverse axis being the x-axis, or which passes through A and A dash, and conjugate axis is about y-axis which passes through B and B dash. So here the length of transverse axis is given by A dash, which is equal to 2A units. out here, and the length of conjugate axis is BB dash, which is 2B, and therefore the length of conjugate axis, that is BB dash, is 2B units. Is how we get this in hyperbola. Transverse axis and conjugate axis have their lengths 2A and 2B respectively. Now let's define the chord of the hyperbola. So as we have the standard hyperbola, out here we see that a chord is a line which joins 2 points of the hyperbola. Suppose I take a point P dash out here, and I take a point P out here, so that so this is one of the chord PP dash. Or if I take this with this, I have Q with Q dash, which are chords. So the different types of chords, there are infinitely many chords which we get. So this being a chord, and this also being a chord. So because there are infinitely many points on the hyperbola, there are infinitely many points which act as the chords as pair of points. Therefore, we conclude saying that there exists infinitely many chords for the hyperbola. Is how we identify this property. Now let's take a special case where a chord through center of hyperbola has a very specific geometric property. That is, if I take an hyperbola in standard form, with x-axis and y-axis, then if I take a chord passing through the center of ellipse or the hyperbola, then geometrically, if this is the point of intersection of this line, then it makes, with center of ellipse, this and this will be equal. That is, C bisects PP dash. That is, CP will be equal to CP dash. That is, C bisects P dash. So any chord which passes through the center, then the center bisects that chord, is what we identify as the hyperbolic property. Similarly, if I have this with Q and Q dash, then this will be equal to this as the bisector. And then similarly, if I have R and R dash, then CR will also be equal to CR dash. Therefore, I conclude saying that center of hyperbola bisects every chord that passes through it. Is how I identify the property, geometrical property connecting the center of hyperbola with the chord. Center of hyperbola bisects every chord that passes through it. Any chord I take which passes through the center bisects. This equals this equals this, and this equals this. Is how we understand the geometric property with center of hyperbola connected with the chord.